This short video will present use case 3 in the Smig project, Digitalized ground support. The aim of UC3 is to test, both in lab and in the field, the next generation of smart rock bolts. These devices can connect data about elongation or fractures or even microseismic activity and send that to a big data system. The partners are Boliden Mineral, Uppsala University, Luleå University of Technology and ThingWave. And together we have been working with development and testing of the smart ground support of the future. We call the solution Digitalized ground support. This is based on an IoT approach and it delivers solutions for ground support monitoring. We can also use this technology for example, smart ventilation, positioning, and other type of sensors can also be added to bring further value to mining companies. The core feature of the system is monitoring of rock bolts, which are used for ground support, and the use of IoT and wireless communication provides real-time data that is being transmitted from the rock bolts using either gateways or 5G up to a cloud solution. This picture shows an overview of the entire system, which is currently based on a mesh network technology that is very suitable for mass monitoring of rock bolts. Into the system we also have gateways which collects all the data from all the smart rock bolts and sensor data to our cloud solution where it can be visualized and we can send alarm to the end users. Use case 3 was hit quite hard by COVID, since we were really depending on access to mines in order to do field tests. But in the beginning of the pandemic, all the mines shut access to external visitors, so we were forced to do more lab testing. But even with that, we did manage to get a lot of results. Perhaps the most important things were the rock bolt sensors. So we have done a few generations and also including patents. We managed to do data storage using the Arrowhead framework. We were allowed to come to one mine in New Zealand before the pandemic and managed to get some data there. We have also done field testing with both Boliden and LKAB. We have results for seismic processing from Uppsala University. We did one experiment with the Salpi project to integrate data from a completely different environment into our environment in Smig using Arrowhead. And recently we were developing completely new sensor solutions for ground support monitoring and we are working with patents. This plot shows the result from a field test that we managed to do together with Oceana Gold in their gold mine in New Zealand. So we were hoping to be able to catch either some seismic data or mining activities just to have a good understanding of how sensitive our sensors are. This picture shows a photograph from one of the field tests that we managed to do together with LKAB in the Malmberget mine. We dropped some rocks from different heights and we managed to pick up vibrations, which was a success. As this plot shows, we can clearly see when even small rocks impact the tunnel floor and our sensors picked it up and can send an alarm in real time to the mining company so they can go in and investigate or reinforce. One main focus of use case 3 have of course been the rock bolt or the smart rock bolt device. So we have put a lot of effort into developing this technology in order to make it more energy efficient so it can live longer on a small battery. Right now we are aiming and we are currently supporting somewhere between 10 and 12 years on a single battery. We can pick up changes in in the rock bolt and send that wirelessly to gateways, which in turn sends the data to our cloud service. One requirement for this technology to actually be usable is that it must support to be automatically installed by bolting rigs. And we have successfully tested this with an Epiroc Boltic. We were planning to do large-scale testing, but due to COVID, we had to put those plans on ice since all the mines were not allowing external visitors. But we did manage to do one test, and it was very successful. We have created a lot of new technologies. We did submit one patent, and we have currently 2 more patents to be submitted. Since it was very hard to have access to active mines, we decided to use different type of sounds or vibration signals in order to train our AI-based follow ground classifier. So we used sounds that we could either find online, such as jackhammers or drills. We even used a coffee machine since it was widely available, and every time we made a cup of coffee, we were collecting the sound and vibrations, and we trained our AI to recognize the sound of a cup of coffee being made. And the plan is when we do have access to mines, we will train the AI on real mine data. So now my colleague Max will present the work with our AI-based fog classifier.
Hello and welcome to this audio classification demo by ThingWave. We have 3 categories to present. We have the water hammer, jackhammer, and the coffee machine. So we have trained an AI model to predict and classify the sound of these 3 machines. So first up we have the water hammer. You can see the water hammer graph and the audio to the left, and we will hear it shortly. So that was the water hammer. And if we proceed to the jackhammer, and lastly the coffee machine, that have a very distinct sound. And as y'all can hear, all these sounds have a pretty similar noise, but not that hard for us to separate. So the question is, will an AI model be able to separate these 3 sounds? And so the goal of this is to then classify rockfall or other types of mining applications where an IoT device with this built into it would benefit. Each of these 3 sounds that we just heard will be sent over MQTT with the audio and a response topic. So the model will receive the data, classify it, and then send it to the response destination, where it, in this case, is a made-up MAC address of the device itself. As you can see here, we sent the coffee audio over MQTT. That's the first package you can see there. And then the 1337 ABC is the made-up MAC address with the class as a coffee machine. Next up is the jackhammer that we will send here. And we can see the model thinking, trying to predict what it is. And this time varies significantly between the amount of information that's stored in the audio, so how large each file is, then the duration and so on. And there we got it, the jackhammer, so that's nice. And if we proceed to the water hammer, which is a slightly shorter clip, so that will take a lot shorter. And there we go, a water hammer.
What we can see on this slide is results from the seismic analytics performed by Uppsala University. So ThingWave managed to, together with Boliden, collect some data from falling rocks, and we sent that to Uppsala University. So here we can see some of the analytics where we can clearly see when the impact happens, and running analytics algorithms, they were actually managed to automatically detect when these type of things happen. And of course, this is very important for a mining company to know, since if small rocks start to fall, bigger ones can actually follow. So to summarize the current state, that all the planned tasks in use case 3 have been completed, except the activities that required mine access, which was limited due to COVID. We did manage to both develop, install and test the new smart rock bolts with an Epiroc Boltec machine, and this was done successfully together with LKAB. We also managed to test seismic sensing together with Boliden and Uppsala University and ThingWave. We also were using Arrowhead, and we did a very successful integration where we could exchange data in both directions between ThingWave Cloud and an Arrowhead local cloud. Furthermore, the whole system with smart rock bolts were demonstrated by Epiroc in the Underground Operators exhibition in Perth, Australia, and it did receive a lot of really good attention from the mining industry. So this was the presentation for use case 3, and thank you so much for listening.